Hello, everyone. Welcome to today's webinar. My name is Khalil Doheny. I'm the Senior Content Marketing Manager at Digital Niche Agency. Today, I have the team of AtomBeam, Charles and Josh. How are you guys doing today?
Good, good.
Oh, great.
Yeah.
Awesome. While people are coming in, Charles, do you want to kind of give a quick background of yourself? I know, there's people here that already know about you, but, if there are any new attendees, it'd be great to kind of just give a quick background. And if you want to introduce Josh as well.
Yeah. I'm Charles Yeomans, CEO of AtomBeam, and one of the founders. So really, my background is pretty varied. I mean, I have an MBA from Stanford, but I was also an intelligence officer for the Navy, and I was a Wall Streeter and so forth. But sort of settled in, and this is my third job as a CEO of technology type company. So it's there's no such thing as everything for sure, but there is, like, I've experienced an awful lot of the things you encounter before. So Josh, and Josh, I should say, introduce him quickly. He is our Chief Scientific Officer, and he is also the guy who took the idea of the other founder, Bhaskar Vyahi, and turned it into a real piece of code. So, Josh, do you want to talk a little about yourself and the other professor?
I'm a mathematics professor, University of South Carolina, and really my work is in discrete math, but a whole lot of topics that bridge with computer science, so machine learning and various topics in optimization and information theory, which is eminently the bread and butter for AtomBeam.
Awesome. And Charles, I know you have a presentation that you would like to share with everyone today. We're going to show that presentation. And if you have a question throughout that presentation, please leave them in the chat box below, and we'll be sure to ask it here. Also, just a reminder, everyone, AtomBeam is currently running a campaign on Start Engine. I highly recommend, everyone to check it out. I'm going to add the link here in the chat box. So if there are any questions, regarding the financials, regarding future projections, anything terms related, please check out that Start Engine page. Unfortunately, on this webinar, we are not able to speak on those questions. So if you want anything related to the terms, please visit the Start Engine page.
Absolutely. All right. Thanks, Khalil. So I'll get my presentation going here. But here's basically, this is a dedicated presentation that's intended just to address this webinar today, but it has a lot of interesting stuff in it that I think this will be a really interesting presentation. And part of it is sort of like, really, because we have Josh here, and we don't unfortunately have him the whole time. We have him for the first 25 minutes of it, but he's going to talk about the science behind this and how the product evolves. And I'm going to move on to address the customers and questions we can take throughout. So quickly on Josh, as he mentioned, he is a mathematician, and he is a brilliant scientist. And he took what was a incredibly original idea and turned it into, honest to God, it works code. And he's, and this is obviously his background, MIT undergrad and a PhD from UCSD. So Josh, do you want to take over from here and just talk through the slides and tell me when you're ready to move to the next slide?
Yep, thanks. Charles asked me, like you said, to join today to give a kind of scientific perspective on some of our upcoming exciting developments, particularly as regards the evolution of the technology. So let me just set the scene a little bit here. I want you to think about the context for kind of our whole world of computing around us. in a sense, you could think of it in two categories. There's computation, where some sort of transformation, some output is being computed from an input. And then on the other hand, communication, right, where bits, bytes, files are being passed around. And given that kind of twofold way of viewing the way that computing works these days, there's an infinitude of levels where your data might be operating. So at some level, the very bottom of things where electrons are just zipping around, you've got zeros and ones, and then at the far other end of things, at the complexity of the data types, you've got semantic level computation and communications, where the goal is interoperability with human cognition. At the bit level, you've got things like, well, our offering, compaction, and related technologies like compression and encryption. And then, maybe as a sort of intermediate level, there's analytics and the massive amount of processing and traffic that goes on inside data centers, the internals of computers and the systems that are built from them, and databases. And then sort of at the high end of the complexity scale here, think of modern machine learning, AI applications, deep learning, newsworthy topics like ChatGPT. And then, from the perspective of communication, at the bit level, you've got things like machine-to-machine communications, the kind of huge amounts of chatter that's going on between devices and even within a device between their components. And in particular, the intra-chip communications that happen on a board or in a chip. And then at a sort of mid-level, you might think about the Internet of Things, the kind of communication that goes on there, and the type of data and complexity that's being passed around, or even just Internet protocol, and of course things like satellite communications. And then at the most complicated end of things, think of speech recognition, augmented reality, brain interfaces, et cetera. AtomBeam really operates at the very base level of this picture. So we are, and this is really fundamental to its applicability to different scenarios, we're really just operating on zeros and ones. It's the very bottom bit level of data, which confers tremendous applicability because, of course, all data ultimately, if you drill down, is made of zeros and ones. So we're operating at that level of things. In advance, just to give you a kind of visualization. So AtomBeam is in the business of taking data and making it smaller. Now, there's a lot of different approaches to this, some that go back to the mid-20th century. And in general, right, the goals are things like reducing bandwidth usage, reducing storage use, things like that. But we're different in a number of ways. And we'll get into some of the ways that AtomBeam differs from the other technologies that have been around for, well, depends, some of them for decades, others for a few years. Here's an example. This is a record obtained from I think this is a single transaction, a single user transaction. So there's a bunch of data about the user and about the metadata of the purchase and some ID associated with it. Lots of data associated with just that single transaction. So we run it through AtomBeam software, and it performs a transformation on these 13,000 bytes. And outcomes, you can advance to the next slide. Well, just over 1,000 bytes. So this little picture, you could zoom in to the next slide. This is it's a rendering. It's if you run the data through a display engine that's treating it like a document. This is the output. Ultimately, what's happening is you've got this ASCII file to begin with. That's of course it's backed by zeros and ones because those ASCII characters are all bytes. But when we apply compaction to it, the output is a bit stream, just a string of zeros and ones that's much smaller. In this case, it was 91.5% smaller than the original data, but is now a binary file that is very, very much like noise. So if you dig into it, you'd see essentially random zeros and ones. And so when you try to render it as a document, just to display sort of for a size comparison, you see some sort of nonsense like this because it's being displayed as Unicode and et cetera. Because ultimately it's just some binary noise behind the scenes that is this compacted version of the original data. Which, by the way, a key point to make about this is that it's entirely lossless, this process. So what you're looking at right now has all of the information from the original data baked into it, but of course in a very obscure way. It's all there, and you can recover bit for bit the original data by decompacting this data using AtomBeam software. Next. So just talk a little bit about what the vision is for where we're going with this. We'll talk a little bit about the ability to search compacted data and a related feature called random access. And then we'll talk a bit about what it means to introduce security. So the AtomBeam system is introducing security into a lot of contexts where it just doesn't exist today. But it's super lightweight, and so again has broad applicability. And then finally, we'll talk a little bit about a kind of medium to long-term goal of ultimately building AtomBeam into an IP core that can reside pretty much anywhere that the computation is happening, which of course there's pretty much everywhere in our world. Next. So first, yeah, searchability. There's a problem with the various types of data reduction technologies that are out there today. Namely, the data is not usable at rest. Once you've reduced the data to some representation of it, it becomes the spread of information across the file is makes it prohibitive to figure out what you're looking at without just turning it back into the original data. A kind of holy grail in compression topics, there's a wide variety of topics that one could reasonably characterize as compression. One of the holy grails that's really not been delivered on is the ability to search the data in its reduced form. Well, compaction does that today. So we can take any file and apply AtomBeam compaction to it. The output is a much smaller file, but it's possible to directly read the contents of the original file from the compacted data without decompacting. Of course, the data that you're reading, the particulars of the data you're looking at are going to be decompacted so they're human readable, but you don't have to decompact or decompress the entire file in order to read subsegments of it. So, of course, this has a tremendous number of users could benefit from the searchability of compacted data. If you think about big pharma with huge amounts of data, that various transcriptions of macromolecules, representations of large data sets, tremendous amount of data that they're storing, and they have to make a choice. Do we use a ton of hard drive space to store this stuff, or do we use less and save money on bandwidth and storage space, but make it unreadable as is? And we'd have you'd have to index it all, find the piece of data you're looking for, and then decompress it and then read it. That's a choice that AtomBeam technology circumvents. DoD also has similar needs. So they've got huge amounts of data, and there's always a decision. Do we store this as is, which is going to take a huge amount of space, or do we try to shrink it down, but then make it so that you can't directly read it? And a significant cost, whether time or literal dollars, is needed to read anything, because you'd have to go into the portion of the data that you're looking for and decompress a big chunk of it in order to read just whatever little bit you're looking for. And of course, you want to run analytics on the whole set of data, then you've got a problem, because that means decompacting or decompressing the entire data set. But with AtomBeam compaction, it's possible to run the analytics directly. Database management operators, think of Splunk or a Snowflake, that are managing huge data lakes and the communications between them and the access points to those data sources. All the folks working in that sort of space could benefit from having searchable reduced data. So we're able to compact the data, and then without having to decompress the whole thing, the user could dig directly into the reduced data set and read it. And like I said, even run analytics on it. So clearly there's quite a number of other, you could probably think right off the top of your head, several other industries where these sort of capabilities would be useful. Next. Another major issue with, in particular, IoT today, Internet of Things communications, is that 98% of it today has no security. This is a giant headache for privacy and for safety. That all of this data flying around between devices, whether it's home electronics or factory sensors, et cetera, is unencrypted. And so an eavesdropper can read any of it or potentially perform injection attacks and disrupt whatever operations are involved. AtomBeam addresses this. The thing is that why not use encryption in IoT? You might wonder, why are all these folks, 98% of this data, why is it not being encrypted? Well, there's technical barriers for a number of reasons. The architecture of most modern encryption is designed to ingest large chunks of data at a time. It's not really designed for short bursts. Encryption requires computation, and in some cases really significant, to the point that it could add to the power requirements of the devices involved. It could add to the latency of the computation or the data access involved, and it can add to the sophistication of the computation needed, the available instruction set. Conversely, compaction adds zero cost and essentially zero compute to security, because the protocol automatically adds a kind of deep obfuscation to the data that makes it very difficult for in particular a casual attacker to eavesdrop or to perform any kind of injection attack. We've also got in the works another project that's nearing fruition at this point, called Compaction Plus, where we're able to actually do a provable encryption at the same time. It's one-step encryption, because you could always take compacted data and encrypt it afterwards, but this is encrypting as you compact. So the data not only is reduced in size, but it's obfuscated in a way that's hardened to all but the most determined attackers, and in a way that's comparable to other modern encryption standards. Next. And then as a sort of longer term goal, we're looking at building compaction into an IP core in order to scale up the technology so that it's available to really anybody that has a processor. So an IP core, this is a tiny add-on that is a modular component of processors. The idea is you're going to bake an AtomBeam chip into the wafer where other computation is occurring, and this AtomBeam compaction IP core is going to provide a kind of turbo capability. The idea is that your computer, one of the big bottlenecks is just moving data around. There are bandwidth bottlenecks, there are timing bottlenecks that are presented by the enormity of data that has to be handled by modern computing. By having AtomBeam available on chip, you're able to apply compaction in all kinds of contexts where the bottleneck is because of the need to move data. And because we typically see, these are just a typical number across different kinds of data, we typically see a 75% reduction in data size, which means, well, if you've got a quarter of the data, then these bottlenecks are sped up by a factor of 4. It can make a huge difference, whether you're talking about AI or very simple processing that's happening in sensors. All of these situations can be accelerated by the addition of AtomBeam IP core.
And you're talking about, just to be really clear, so I buy a new phone, I buy a new laptop, this could be something in that laptop, in all the different processors in that laptop.
That's right. Yeah, if you think about a end user, consumer end user. They're not even aware of what the chip that's running your devices has on it. But the manufacturer and the service provider certainly know about it and get some value added by adding AtomBeam into the processing in order to improve its speed essentially for free.
So this is different than what we usually talk about, which is moving the data from, a phone to or from some machine into another machine or something. This is inside the computer, making it faster in and of itself.
That's right. Yeah, think about the communications between memory and the main processor in the phone, or between sensors on the device, whether microphone or battery sensors, et cetera, or even just between the components of the main processing unit that's running the phone.
Or even between servers in a data center or something, right?
Absolutely.
So if you were to say, for example, okay, I have a super fast processor on my laptop. The limiting factor of the speed of the computer overall is not necessarily the speed of that processor. It might be pathways. It might be the thing moving the data from whatever to whatever.
Absolutely. Yeah. So for quite a number of the kinds of operations that modern computing machinery is performing, it's really the bandwidth between devices that ends up being the constraint.
Right. And so literally, this could be added to virtually all processors, put onto logic boards, and then, yeah, those processors, the extra core, which is like, you're always reading about 32 cores in this or that CPU. And so you're adding another core. It's a specialized core that has compaction built in, and it would allow every computer to overcome the constraint that is moving the data from here to there, and therefore overall that computer could be significantly faster.
That's right.
That's great. So, I got to tell you, because, we don't really address this mostly, but we have a patent for it, and it is something that is in the works. And this is the IP core approach is something that could translate into literally billions of copies of compaction. And, you think about the impact of this. If Intel is able to say to anybody else, well, you buy our chip and it's got this in it and it's going to go faster, not only in the moving data to the cloud or something, but also the whole computer's faster, which is pretty freaking dramatic.
Absolutely.
Yeah. So go ahead.
Yeah. So just to give a kind of picture of what, how to think about scaling this technology up. We think of this as sort of three regimes. There's at one end of things where a user has hundreds or thousands of devices, maybe. It's enough for them to use the software development kit, SDK, or even a cloud interface to AtomBeam to perform compaction and decompaction, because, well, they're able to maintain and deploy on a comparatively small number of devices. Think of a Saab who has used AtomBeam, thinking about deploying it on hundreds or thousands of airplanes. In the middle range, we've got the kinds of users who have maybe millions of devices. Here you might think of someone like a Caterpillar, who has millions of tractors and bulldozers and all kinds of different equipment out there in the field, and chips within those devices. And it would be difficult for them to deploy and to maintain AtomBeam on all of those different devices. So what we're currently working on is developing a single board computer SBC version of AtomBeam, where the user can just have it might be an FPGA appliance as well. Just have a dongle, a device you just plug into a USB socket, or becomes an insert into a communications line that transparently performs AtomBeam compaction and or decompaction. Mostly we're thinking about compaction because often the decompaction is happening at a centralized server on millions of devices with essentially no intervention by the user, just transparently processing the data into compacted form. This would allow a user who's got, say, millions of devices to easily deploy it to all of their technologies. And then at the far end of things, you've got billions of devices. Think about chip manufacturers, anybody that's got chips, wafers, computers in large numbers. In this case, it's still too much to try to plug in a physical device into each of the components that could benefit from compaction. Instead, we build, and this is in the works, to build AtomBeam into an ASIC, essentially a bespoke chip that can perform the computations required for AtomBeam to operate. Or relatedly, as we were just talking about, IP cores. So having a component that can be attached as a modular component of a chip in order to benefit the rest of the operations that are occurring in that chip. That would allow billions of processors to use AtomBeam. And
Seems
then
like we have a question that just came in.
Yeah.
If AtomBeam existed on a processor, where would the code book be stored? Does the code book have to regenerate if you restart the computer?
So yeah, I mean, there's a number of different options here. One is to have a non-volatile memory that stores the code book. In another incarnation, for example, some FPGA applications, there's onboard RAM that stores the code book and then accesses a server on occasion to update it. We have a kind of beta version of a dynamic codebook capability to do exactly that. So it depends on the use case and the user's ability to deploy codebooks to the devices that have AtomBeam running on them. This is just a kind of visualization of some of the use cases and areas that we might be moving into as the technology moves from SDK to SBC to FPGA to ASIC to IP core. At the one end of things, you've got folks like satellite communications and IoT, where battery life and communications range and reduction in data size are really key to, for example, defense or internet data lakes, where search and random access are really key. And then you've got folks like intelligence, where the encryption capabilities are going to be really important to them. In accelerated computing, where this is to enable faster computations in GPUs or between large data centers, where the data reduction is going to be absolutely key to getting the benefits of speeding up and making better use of bandwidth. So it's just a number of different use cases enabled by this evolution of the technology from today's version and SDK to physical devices and FPGAs all the way to IP cores.
Right. And Josh, I know you have a commitment that you have to go. And so thank you very much for spending the time here. I think anybody who's attending this is going to agree that it was super helpful and really clarifies things. So thanks for doing this.
Absolutely. Thanks very much.
Okay, so we are going to keep going. I do have a question there, Khalil, and I hope it wasn't a Josh question. If so, I'll do the best I can.
Let's see. In an environment where multiple endpoints need to communicate with each other, e.g., military aircraft, weapon systems, etc., would they all share a common code book, or would each pair have to have a unique one? This could amount to a lot of CPU, RAM, etc. usage.
Yeah, no, in order for aircraft A to communicate with aircraft B, you got to have the same code book. And so, yes, necessarily they would each one have the same code book, built into their system. And you could have it update on a regular basis on some sort of schedule or whatever, but yeah, they would all, for example, there's one of the big topics out there right now is the military overall. I mean, including Navy, Army, Air Force, Space Force, all communicate using this thing called Link 16. Link 16 is 3158, or I think it's 111 kilobytes per second. And so it's really slow, and they're desperately trying to find out ways of making it faster. To give you an instance, that, I've had a two-star general, a Navy officer, all these other people say, we need to figure out something here. And we're in discussions right now about how to do that. So that, to be able to make that happen, what we would need to do in terms of actually making that work would be to either give them some sort of small form of an SBC, a single board computer, or more likely an FPGA, which is essentially the same thing, except it's all on one little chip. And so you would plug the thing into, with that code book, with the same code book, into this thing and that thing and this other thing. And then all these things would have the same code book, and they would all communicate, and they would all be, compatible. So, but it would vary to say, okay, but I want to send data from this kind of a, this medical data or whatever. And yeah, they would have a different, they would have different code books depending, but yes, fundamentally you need the same code book on both sides of the equation.
Awesome.
Okay. So moving along, to talk a little more specifics about how this really evolves in terms of turning it into something that I think gets us, into the market very much, much more effectively. And so we think about what we have now, and Josh talked about the SDK, the software development kit. And that's basically, here's a little group of, the actual code, as to say, the executable, not the source code, but the executable, some testing software, instruction manual, stuff like that. And that's good. If you're Saab, that's just what you want, because you're going to do the integration, you're going to do all that stuff. Whereas, somebody else, that may not be the right thing, as Josh was saying. We've also loaded it into a Raspberry Pi, which is a kind of simple SBC, so a single board computer. And we also have our web-based interface. So that's the manifestations today. So where we really need to be, and where, we're working on right now, is getting it into a really industrial strength SBC. And that can be done in parallel with the work to get it into an FPGA. So the FPGA is basically, a chip, right? But the programming work that you do is pretty similar for both. And You need to get to the FPGA, both because you like the small form factor and all that, but the FPGA is field programmable gated array. And so it's programmable. That's the big difference between that and an ASIC or IP core, because you can change the code on it. Whereas once you make, you code an ASIC or an IP core, that's it. You can't change anything. It is what it is. It's built to, and so if you take the ASIC example, that's an application specific integrated circuit. What that does is one thing and one thing only, in this case, compaction. You might, if you open your phone up, you look in the back, a lot of those chips are ASICs. And what they're doing is they're saying, okay, I can translate human speech into text or something. That's specifically what it does. And so we would have an ASIC. Oh, an ASIC is a big project, it's like millions of dollars. But getting to an FPGA up and running, that's how you figure out, okay, I need to fix that. That isn't quite right. Everything has to be 100% bulletproof before you move it to an ASIC. And so it's a necessary intermediate step. And the cool thing is both the SBC and the FPGA are both saleable products. We can put them out there and, people will buy them. And not only that, I can get over a big hump with a lot of guys if I can say, here, for very small dollars, buy, 5 SBCs and plug them in, and then you can try it. That would get me a huge hump. And our partners are going to be critical to that. The commercial partners in Marsat and Intel and Cribble, and Crosser and CrowdPoint, they're all like really keen on getting those physical boxes to have it. And then, Lockheed is super supportive, really wants to work with us on this. And we just had a conversation with a guy at DoD who's in the Air Force who wants to support the FPGA effort. And talking again about Link 16, that is how you test it in the field, get it in things fast and all that. So that kind of lays out the whole thing with the whys and wherefores of putting it into a physical device. So anything before we move?
Yes, we have 2 questions. This first question is a 3-part question.
Okay.
First part of the question is, I work in cybersecurity, and with IoT and see a million of use cases. You touched on searchable data with Splunk, but for systems that have been compromised at a chip level, would compaction obfuscate discovery of that rogue data, or will the future chip level implementations assist with that? That's the first part of the question.
Sheesh. That's only one part.
Yep.
Okay, I'll do the best I can. That this was really a Josh thing. So, so I would mention a couple of things. One, on the obfuscation part. So really what we're talking about is what was initially people said, well, it's just a substitution cipher, like this equals that kind of thing. But if you consider the fact that we're talking about representations of patterns, and the numbers of these representations is in the many thousands, even millions, it's a very tough computational task to try to break into a code book, simply because there's just so much randomness, and you're just looking for patterns instead of like, this code means that letter or something, something in the real world. So it's heavily obscured. And then, I'll mention one more thing, and then I probably need the question read again just to make sure I'm addressing it. But one thing we do that Josh has architected is intrusion detection. And the way that would work is we look at the flow of data, we look at the amount of compaction we're getting, and then we look for unusual behaviors, too much, too little, too flat, too this, too that. It's a non-metrical comparison called Kale divergence that he would apply. So anyway, read the question again and let me see if I've sort of kind of answered it, and I'm happy to ask Josh. So, but go ahead.
Yeah, so would compaction obfuscate discovery of that rogue data, or will the future chip level implementations assist with that?
I think the answer is yes, we would note the presence of the rogue data because of the intrusion detection. And with respect to the chip level, yeah, I mean, that would spread it out to a really, you know, you'd have it in everything, and therefore you'd be looking in everything, assuming you implement the intrusion detection on all those things. So I mean, I think the answer is yes, we would address it, but I'd be happy to refer to Josh to be sure that I'm not off base here, but go ahead.
Yep, and the second part of the question is, just heard you mention it might live in RAM, but would it tie into hard-coded TPM chips?
Boy, I don't know the answer to that one. I can, let me paraphrase something that Josh is, unfortunately, I'm not an engineer, and this guy knows what he's talking about. So I would say this, that Josh has talked in the past about, okay, what about if you're talking especially a military thing and somebody captured something that had our, you know, a code book in it, and now suddenly they can read our stuff and we weren't aware of it. And so suddenly now they can read it. So the way he said that you would deal with that is you would encrypt the code book in storage, and then when you're actually using it, you would decrypt it and put it into the RAM. So read the question again, and see if I'm even getting anywhere close.
Just heard you mention it might live in RAM, but would it tie into the hard-coded TPM chips?
I think it, I mean, look, it can get hard coded in anywhere, right? And you know, one of the things that you have to consider when you think about how you what you're hard coding, the executable can be hard coded. You can hard code the code book too, but you may not want to, simply because you want to update it. Okay, I've updated the system software or something, and I need to change the code book now. So usually how we think about it is like you've hard coded the executable, and the software, I'm sorry, the code book lives in some version of RAM.
And then the third part of the question is, AtomBeam focuses on data in transmission and no mention for storage like data at Library of Congress. Can compaction compete with data at rest compression algorithms?
Yeah, well, I mean, I would say this, that generally, yes. I would say that because, so one key thing to remember here is we're only touching the payloads of these data. And so we leave the headers intact. And so when you store, you know, like terabytes, petabytes of this data, we usually underperform when you're talking massive quantities of data compared to, you know, a state-of-the-art compression or compression plus dedupe. So we're usually not going to get, you know, if they're getting, you know, 80%, we might get 72%. It's kind of that, like that. But, you know, the trade-off is, say you're doing DNA research, and instead of having to decompress 1 million genomes, 3 billion base pairs for humans, to look at 12 base pairs on 1 million genomes, you can just type in a search term. And so there's a trade-off. Yeah, I mean, but at the same time, to make all that data at rest useful, compared to, okay, I'm going to need 10% more storage or something, most, I think, or a lot of people would say that's worth it.
And then the last question here. So if I am providing IT services to the government, would I need a separate code book for each agency?
You would need a separate code book for each kind of data. So if, for example, you were sending data from an F-35, well, it depends on the type of data link, right? And so if you were talking link 16, yeah, you need a link 16 code book that's based on the data that link 16 generates, as opposed to saying, okay, I need a code book to go from this set of refrigerators or from this agriculture thing or something to somewhere else. Yeah, that's a different code book. And that's why this super automated code book generation, this dynamic code book that Josh mentioned, that's why that's so critical. We need that to be in place so that everything is hands off, everything's automatic, nobody sees anything operate, everything just happens.
There aren't any other questions at the moment, so if you want to continue
Okay,
the presentation.
Okay, so, we already talked about this kind of already, but fundamentally, we're really talking about this as a project that we have cranking up now. And it's really this in parallel with the FPGA project, because it's similar kinds of development project. And once you have that, you can take it hand in, and guy at Caterpillar, he could take the thing, put it into his connected dump truck, and now that dump truck can send a quarter less data, and it's secured. And I got to tell you, if I had these today, I'd be selling these like crazy. This is this is a lot. I don't think it's all of the big companies, not including like some of the ones that have interest mainly in the searchability thing, like some of the pharma ones. But these are the companies that have engaged with us one way or another, talk to us, want to, talk about, get excited about it and all that stuff. If I have this SBC, I can go back to all of these guys and say, hey, a few $1,000, buy a few of these, plug them in. You can try it out. And the impact of that, I can't tell you. I mean, I talked to these guys in many cases, and I asked them, what if we had this? What would you say? Would you do it? And they, so far, I haven't had any no's. So that's why this is a key project, and that's why I'm so focused on it. So,
how do you prevent false positives so good data won't get identified as rogue data?
well, like false positives. So bottom line is that if it translates to, we don't lose any data, right? And so if it translates back to the normal data that you were getting before and fully 100% no loss, then it's good. And if it is doing anything other than that, it's not good. So there isn't really any issue with false positives. So anyway, so just really quickly, we talked about this before, but we are actively working with all these guys, Cribble, and we're jointly proposing to a Navy crosser right now. We have some stuff going on in with smart buildings, Lockheed, Inmarsat, Intel, Lockheed. We're working on a deal right now with Air Force, Inmarsat. They want to deepen the partnership, and thank God, finally, they're going to put us on the website. I think that'll happen in the next couple of weeks. Intel's a new one, and Intel could be very, very interesting because of all the stuff we've been talking about with ASICs and IP cores and everything. But it's early days with them, but I think that was the source of their interest in us. So Saab, they're supposed to start moving it into this quarter into start their process of field test. CrowdPoint, I've been like cranking on that lately. Insight Terra is actually using it, the Inmarsat satellites, they're an affiliate and they're using our stuff. And then we have phase 1 with the Air Force and a phase 2 that we were selected, not funded, but we have active dialogue going right now that could end up getting it funded. Really quickly on Air Force, just generally, they have really focused on this Link 16 thing. We also are working with them on another project. It's mostly on synthetic aperture radar beta, which sounds kind of exotic, but fundamentally it's like these giant files that are like 200 megabytes each. And if you use compression on it, it takes 30 seconds to do the compressing and decompressing. And we're like less than a second, maybe 3/4 of a second. And so if you have like a missile coming at you, you'd like to know a lot sooner rather than later. And so they have, so they're pretty excited about our stuff. So then so we just have a lot of activity going there. We have a Navy guy, a Navy officer reached out to us from the Pacific Fleet. And I already mentioned the Cribble thing, but they're interested also in this Link 16 thing. So Link 16 could turn into being something pretty significant.
What does a partnership with Intel actually mean, and how did the partnership come about?
Yeah, so that was initiated actually by Ashkar Yahi, the CTO and co-founder. So Ashkar had been talking to them for a while about how basically engaging with some of their engineering guys, and they kept pushing it up to higher levels, and finally said, look, we need to establish some sort of formal partnership because we see some potential here. And we want to understand the technology better. And we see opportunities for Intel to benefit, maybe in the context of putting it into ASICs and so forth. What are they trying to do? They're trying to sell more chips, right? If they have chips with our stuff and people think that's better than chips that don't, then they'll sell more chips, and that's the whole point for them. So I want to be careful and say it's early days. We're just getting going with those guys. We're in, but we are getting attention. They did partner with us. It is very promising, but again, early days.
There aren't any other, let me see if there's this. I also invested 2 years ago, long-term. Are you thinking to make SBCs and IPOs, sell the company or license? I know we have to be very careful how we answer this question. So yeah, Charles, I'll let you be as vague as possible with it.
Right. Yeah. I mean, we are obviously, as Khalil's saying, we're pretty constrained in what we can say, about future stuff and, IPOs and all that. I would say this, that one of the things that is a factor out there is that let me repeat a conversation, paraphrase a conversation that I had with Lockheed. So Lockheed said, a guy who's a space guy at Lockheed, pretty senior, said, look, if we had your stuff and our competitors didn't, and we're bidding for a contract with Space Force for putting a couple of $1 billion worth of satellites up, and we can deliver 4 times more bandwidth, well, guess what? We're going to win that contract. And that means billions of dollars of value delivered to Lockheed because we have your technology and other guys don't. So, and then, conversations about investing and, and so forth. But, I can't go into, really the detail that unfortunately that is being asked. So.
Awesome. I'm not seeing any other questions coming in. I am going to add the Start Engine page link one more time here in the chat box. Charles, are there any final words you want to leave the audience with today?
Yeah. So I would say it's great that, we had a chance to hear from Josh and to also get some questions that were very, not deep knowledge kind of guide questions. And if I would ask, if you wouldn't mind, you can either send them to me, send them to info@atombeamtech.com, and I'll pass them along to Josh. Or if you want, post them on the Start Engine site in the chat, in the section that the discussion section. Any of those works. So we are, we're very, I got to tell you, every time we come up with something, I mean, it's like Josh was saying right in the beginning about bit level. When you're down at that level, it's hard to even think about. I mean, most of the things that we've come up with have emerged. They didn't understand, didn't think about it, didn't realize. And then it's a voyage of discovery. And it's like, why wouldn't it do that? Well, I guess it would. And so then we move on to the next thing and the next thing and the next thing. And then we file patents. So 18 patents, another 13, I think, pending. So we've got a lot of stuff. And I think this could be a game-changing, billions of things technology. It's hard to get it going. But I think with this SBC and the FPGA effort, we can really start to move it.
And then I'm seeing 2 questions here. The first question is, are you planning on doing a few more raises on Start Engine, or is this the last one? Like we mentioned, we can't speak about future things happening, but I will say this: why wait? Why wait till the next one? If there is going to be a next one, get in today, get in early. Be in the front of what AtomBeam is doing. Get in, now before you don't know what's going to happen down the line. So, why wait? And then another question is today's slides available? Yes, this whole webinar has been recorded. So we are going to be planning posting a recap video around the webinar. So be on the lookout for that on the Start Engine page as well.
Yep. And so I just want to thank everybody for coming in and spending an hour with us. I mean, it's, I mean, personally, yeah, it's been a journey in a lot of ways, pretty hard and everything, but I just to be a part of, either as a member of the team, an investor, things are real. This is going to be a game. I mean, everybody talks about game changers. Well, bullshit. This is a game changer. This is really going to change stuff. It's going to be in every freaking thing on the planet. Awesome. I think I'm supposed to add that. I think.
Awesome. Well, thank you, Charles.
Thank you.
When you see Josh, say thank you to him as well. And
will.
yeah, I hope everyone has a great weekend. Talk to
All
you
right.
soon.
Thanks. And we'll get I'll get the notes the people post sent to me. So,
Perfect. Have a
all
good
right.
one, guys.
Great. Thank you, everybody. Have a good day. See ya.